Good evening. In this video, we are going to discuss proposition 10 from book 2. This proposition states that if a finite straight line, for example AB, is bisected at the point of C, then another straight line BD is added to straight line AB. Then we have the square on the whole, which means this is the whole, okay? Together with the square on the added straight line, this is another square, will be equal to twice of the square on the half, which will be AC square, plus the square on the straight line, that is the half plus the added one together. So which means square here, CD square. Okay, so let us try to prove this equality. So first of all, let us do some Euclidean construction. So let's apply proposition 11 at first to construct a straight line that is perpendicular to AB through point of C. And then let's apply proposition 3 from book 1 to cut off CE here, that is equal to AC and CB. So if we apply combination 1, we can conclude that AC equals CE equals CB, correct? And then let's use postulate 1 to join AE and BE respectively. Correct. And then let's apply proposition 31 from book 1 to construct two straight lines respectively. The first one is a straight line through point D that is parallel to CE, okay? And another straight line is here through point E that is parallel to AD. And let's assume they are meeting with each other at the point of F, okay? So we know that EF is parallel to AD and CE is parallel to DF, correct? And please have a look at these two angles. Let's make it angle 1 and angle 2, okay? So we know that CE is parallel to DF, correct? And if we apply proposition 29, we know that two interior angles, the sum of them, which means angle CEF plus angle 2, they are two interior angles in the same side of two parallel lines, will be equal to twice of the right angle, correct? And angle 1 is obviously less than angle CEF because of combination 5, the whole is always greater than the part. So if we combine this, we can conclude that angle 1 plus angle 2 will be less than twice of the right angle, correct? And please recall postulate 5. If a straight line is falling on another two straight lines and the sum of two interior angles from the same side is less than two right angles, then these two straight lines will meet with each other on this side, correct? This is postulate 5, which means EB and FD will absolutely meet with each other in this side because the sum of angle 1 and angle 2 are less than two right angles. So let us apply postulate 2 to produce EB and FD respectively, and let's assume they meet each other at the point of G, okay? So this is G. And then let's use postulate 1 again to join AG. Okay, great. So we have finished the Euclidean construction steps, and let's try to prove this equality. Okay. The proof steps are very similar to the previous proposition 9. So let's just repeat them. Okay. So we have, let's give them some marks. Angle 1, 2, 3, 4, 5, and 6, and 7. We know that AC equals CE. Thus, angle 3 equals angle 4 because of proposition 5. Okay, the two angles on the base of an isosceles triangle are equal. Correct? They are equal. Isosceles triangle, so they are equal. And similarly, we can conclude that angle 5 is equal to angle 6. Correct? And if we have a look at this triangle ACE, we know that this is the right angle because they are perpendicular. So, and if we apply proposition 32, we know that angle 3 plus angle 4 is equal to a right angle. Similarly, angle 5 plus angle 6 equals to a right angle, right? So if we combine these four equalities together, we can conclude that these four angles are equal. So we can conclude that angle 3 equals angle 4 equals angle 5 equals angle 6 equals half of the right angle. Besides, we can conclude that this is the right angle, correct? Because it equals to the sum of two half of the right angle, so this is the right angle. So let's write it here. AE is perpendicular to GE, correct? And let's put the conclusion here. Okay. So now let's apply proposition 15 from book 1. We know that vertical angles are equal. So they are two vertical angles, so we know that angle 7 is equal to angle 6, correct? And let's assume this is angle 8. We know that EC is parallel to FG. And if we apply proposition 29, we know that angle 5 will be equal to angle 8, correct? Because they are interior angles from the two opposite sides lying in two parallel lines. Okay, so they are equal. Great. So let us have a look at angle 1. Okay, so since AD is parallel to EF, correct? Then we know that angle 1 is equal to angle 6, correct? Because they are also two opposite interior angles falling in the parallel lines. And if we apply proposition 29, we know they are equal, correct? With these conclusions, we can say that 5 equals 8 and 6 equals to 1, and we already know angle 5 equals to angle 6. So if we combine them together, we can conclude that angle 1 is equal to angle 8, correct? Okay, and angle 7 is also equal to angle 8. And if we apply proposition 6, which is a converse proposition about proposition 5, so if two angles of a triangle are equal, then the two edges subtending them are also equal. So angle 1 equals to angle 8, they are equal. So in this triangle EGF, the two sides are equal. So EF is equal to FG. And in this little triangle BGD, angle 7 equals to angle 8. So it concludes that BD is equal to DG. Great. And let me check. Okay. So let us apply proposition 47, which is called also known as Pythagorean theorem. So in this triangle, have a look at ACE. In this triangle, we have AC squared plus CE squared will be equal to AE squared. And we've already proved that, we constructed that AC is equal to CE. So it also equals twice of AC squared. Okay? So this is another conclusion here. And have a look at this triangle. We have proved angle AEG is a right angle because AE is perpendicular to G. So in this triangle, if we apply Pythagorean theorem, we know that AE squared plus EG squared will be equal to AG squared, correct? Okay. And let's put this equality here in the box. And if we apply proposition 34, we know that the opposite angles of a parallelogram are equal. So CDFE is a parallelogram because they are parallel. We constructed like that. So this is a right angle. So angle 2 must be another right angle. We can make it here because they are opposite angles in a parallelogram. So triangle EFG is another right angle triangle. And if we apply Pythagorean theorem again, we can conclude that the square on the EF and the square on FG together is equal to the square on EG. Correct? This is another equality. And then let us plug in EG here. So we can conclude that AE squared plus EF squared plus FG squared is equal to AG squared. Okay. And we have concluded that EF is equal to FG here, correct? So EF squared plus FG squared will be equal to twice of the EF squared, correct? So it equals to we also know that AE squared is equal to twice of the AC squared. So let us plug this here, and we have twice of the AC squared plus twice of EF squared will be equal to AG squared. Okay. So now let's apply Pythagorean theorem again in this triangle AGD. Let's say AD is parallel to EF, so we have angle BDG is equal to angle 2, correct? Because they are the exterior angle and the interior angle in the opposite side of two parallel lines, so they are equal, which means this is a right angle and ADG is another right angle triangle equals to a right angle. So we have, let's put it in the box, we have AD squared plus DG squared will be equal to AG squared, correct? And if we combine equality 1 and equality 2 together and apply common notion 1, we can see that right sides are the same thing, so the left sides must be equal. So it means, let me write it here. So it means combine 1 and 2, we have twice of AC square plus EF square are equal to AD square plus DG square. Okay? And if we apply proposition 34 again, we know that the opposite sides of a parallelogram are equal. So this is a parallelogram, so EF must be equal to CD, correct? So we have EF is equal to CD, and if we plug CD here to replace EF, we have twice AC square plus CD square will be equal to, let me check, AD square plus DG square. What is DG square? We have proved that DG is equal to BD, correct? And so let's replace DG by BD. So AD square plus BD square, correct? So we have this conclusion. Twice of the square on AC, which is half, plus the square on CD, which is half, as well as the AD straight line, is equal to the square on the whole AD plus the square on the AD straight line BD, which is absolutely equivalent to our proposition. See, they are equivalent. So we have proved our proposition is true. And in the next video, we are going to talk about proposition 11 from book 2. Thanks for watching. Have a good day.